Okay, good afternoon, everybody. My name is Hunter, and this is an early live stream of content review for general chemistry students at Portland State University. Delivering a little bit earlier so that I can make it to an event later this evening that would otherwise conflict. But you all will be watching this in the future, either on the Twitch channel or on the PSU Learning Center YouTube channel. So I'm just going to dive right into this since I don't expect folks to sign in while I'm actually streaming. So we're back in solutions. We're looking at the colligative properties again. You can think of the colligative properties simply as expanding the liquid phase. So for question 42, why does 1 mole of sodium chloride depress the freezing point of 1 kilogram of water almost twice as much as 1 mole of glycerin? There are a couple key hints here. We have 1 mole of sodium chloride and 1 mole of glycerin in our mass of water. And if you remember from last week, moles per kilogram, whoop, moles of solute per kilogram of solvent is a measure of molality. And this is a useful measure because it is uh, independent of temperature, right? And this is kind of getting into exactly why this is a useful measure. The colligative properties depend fully on the total concentration of solute species, that is the number of moles, and not the identity. The reason that sodium chloride depresses the freezing point more than glycerin is because sodium and chloride ions will dissociate in aqueous solution. And so you don't just have you don't just have 1 mole of solute, you actually have 2 moles of that sodium and that chloride dissociating from each other and being surrounded by water molecules. The colligative properties depend entirely on total concentration of solute species and not their identity. The number of particles is greater for the ionic solutes because they dissociate. So for our first quantitative question, assuming ideal solution behavior, what is the boiling point of a solution of 9.04 grams of diiodine in 75.5 grams of benzene, assuming the iodine is non-volatile? Non-volatile meaning it's not going to evaporate out and add its own gas pressure. That's an important term there. So first we need to outline the steps necessary to answer the question, and then we will answer the question. Off to the right here, I've already calculated our molar masses for the benzene and the iodine in question. But the formula that's important here is this one. The change in boiling temperature is the quantity of some boiling constant times molality, which is that moles of solute per kilogram of solvent again. So to get our answer, we first need to convert grams of solute or mass of solute to moles. And grams of solvent to kilograms. Yes, moles per kilogram. That gives us our molality. So calculate molality. And then multiply the boiling constant, which will be tabulated. And this will be the boiling constant of our solvent, so the thing we have more of, by the molality to find the change in boiling temperature. And finally, add that change to the original boiling point. So let's run that down. So starting off, we were given a quantity of 9.04 grams of iodine. Our molar mass was 253.8 grams per 1 mole. Gives us 0.0356 moles of iodine. We're given 75.5 grams of benzene. And that's 78.12 grams. Excuse me. We're not going to moles, we're going to kilograms. So we just divide by 1,000. 1,000 grams per kilogram of benzene gives us 0.0755 kilograms of benzene. Step 3, we calculate our molality. So we have 0.0356 moles of solute divided by 0.0755 kilograms of solvent equals 0.472 moles per kilogram. Finally, we need to look up the tabulated value for the Kb of benzene, which is 2.53, and plug that into our equation here. So the change in boiling temperature equals Kb times molality equals 2. What did I say that was? 53 times 0.472 gives us our change, which is about 1.2, and that'll be degrees Kelvin or degrees Celsius. Finally, if you can't remember whether to add or subtract it from a boiling point or a freezing point, remember that the colligative properties expand the liquid phase. So boiling points will get higher in temperature and freezing points will get lower in temperature so that the liquid phase is in a greater span, a greater absolute value of temperatures. So our new boiling point equals boiling point of benzene is normally 80.1 degrees Celsius. You'll notice we're not dealing with any changes in pressure, so we don't have to worry about that. We can just assume at standard temp, well, yes, at standard temperature pressure. So 80.1 degrees Celsius plus, we calculated 1.2 equals 81.3 degrees Celsius. And that is our answer. So remember, in exams, you will probably need to calculate the molar masses of the substances in question. So kind of remind yourself of how to do that. Make sure you account for all of the species in calculating those molar masses. I'm not doing that in this practice because you should be pretty proficient at this by now. All right. Assuming ideal solution behavior, what is the freezing temperature of a solution of 115 grams of sucrose in 350 grams of water? Outline the steps necessary to answer this question. This is going to be very, very similar. We're just looking at the tabulated values for freezing points and those constants, and we will be subtracting instead of adding our change. Excuse me. So the change in freezing temp is the freezing constant times the molality. Step 1, convert mass solute to moles. Convert grams to kilograms of solvent. Calculate molality. This is different from molarity, which is moles per liter, right? Moles per volume. We're doing moles per mass now compared to last week. We will multiply the freezing constant times our molality to find the change in freezing temp. And finally, we will subtract Kf from, excuse me, not Kf, the change in freezing temp from the original freezing point. Let's run the numbers. So we have 115 grams of sucrose. I've already calculated this for you, but your molar mass is 342.3 grams per 1 mole equals 0.336 moles of sucrose. We have 350 grams of water. Divide by 1,000 grams per kilogram. Gives us 0.35 kilograms of water. 0.336 moles of solute per 0.35 kilograms of solvent gives us our molality, which is 0.96 moles per kilogram. You will sometimes see this written with a -1 exponent, which is the same as saying divide by. And that allows you to type it linearly. So that's just a formatting thing that if it hasn't been explained before, should be aware of. Finally, the freezing constant times the molality equals our change in the freezing temp. And the tabulated value of Kf for the solvent, which is water in this case, is 1.86 times our molality, which is 0.96, gives us a change of 1.79, degrees Celsius. For our final step, we take our original freezing point minus the original freezing point of water is 0 degrees Celsius, which makes this math pretty easy. And so our new freezing temperature is negative 1.79 degrees Celsius. Assuming ideal solution behavior, what is the osmotic pressure of an aqueous solution of 1.64 grams of calcium nitrate? I think that's calcium nitrate. Yes. Aqueous solution of calcium nitrate in water at 25 degrees Celsius. The volume of the solution is 275 milliliters. Outline the steps to solve your equation. So we're solving for something a little bit different here, and I'm going to put the equation off to the right. This is our symbol for osmotic pressure. And the way that I think about this is in the classic example, you have the tube, a U-shaped tube with the semi-permeable membrane in the middle. If I just flip that over, it kind of looks like this symbol. So for calculating osmotic pressure, we're now concerned with molarity again, which is moles of solute per volume of solvent. So this is osmotic pressure. We have moles of solute per liter. We have R is the universal gas constant, which in this case, let me make sure I got that right. I'm trying to do this from memory. 0.08206, yes. And our units, these are important, are liters times atmosphere over moles dot Kelvin. And this is going to make everything cancel out really nicely so that we have the right units for our answer. And our temperature will be in Kelvin. All right. So I see we have a viewer in the stream, which I appreciate you. I'm delivering this a little bit earlier than I normally would so I can make it to an event later. So appreciate everyone being flexible. The excuse me, the recordings will be available, so you can watch from the beginning later if you would like to. All right. So step one, we still need to get to moles. Mass of solute to moles. Step two, we're given a volume in milliliters. We need to get to liters. We can then calculate our molarity. We'll need to convert from Celsius to Kelvin because our universal gas constant is in degrees Kelvin. And finally, multiply to get our osmotic pressure. Okay. So answering the question. Mass solute, we're given 1.64 grams of calcium nitrate, has a molar mass of 164.1 grams per mole, equals 0.00999 moles of calcium nitrate. Step two, milliliters to liters should be pretty simple. Can do this in your head, but we're going to write it out. We're given, was it 275? Yes. Milliliters of water, divide by 1,000 milliliters per 1 liter, equals 0.275 liters of H2O, which gives us our molarity, which is 0.0, I'm going to get that wrong, 0.999 over 0.275 gives us 0.0363 molar. Convert Celsius to Kelvin. So we're given 25 degrees Celsius plus 273.14 if you want to be more precise. For our purposes, we do not need to be. let me rephrase. If your professor wants you to be precise and include that 0.14, include it. It will give you a more precise measurement. For the purposes of this practice, this is close enough. And step 5. We have a molarity of 0.0363 times the gas constant, 0.08206, times the temperature equals our osmotic pressure, which should be 0.889. And I just want to show what our units would be. So bringing this up here, we had moles per liter. For our gas constant, we had, where did my mouse go? Liters, atmosphere, mole, Kelvin, and then a temperature in Kelvin. So we can just put that over 1. And these should all cancel out. Moles cancel out with moles, liters with liters, Kelvin with Kelvin. So we should have units in atmosphere. Now, if you thought we were done, you would be incorrect. Because remember at the top of this worksheet, we talked about how the number of species, the total concentration of the solutes matters more than the identity. And we are dealing with a soluble ionic compound in water. So this is an aqueous solution of calcium and 2 nitrates. This will dissociate in water to be calcium by itself and 2 equivalents of nitrate by itself. So our final answer, we have to multiply by 3, and that will give us 2.67 atmosphere. So be really, really careful about this. Cool. Okay. I think that's everything I needed to talk about for that one. A sample of organic compound and non-electrolyte, so we're not dealing with an ionic compound now, weighing 1.35 grams, lowered the freezing point of 10 grams of benzene by 3.66 degrees Celsius. Assuming ideal solution behavior, calculate the molar mass of the compound. So this is a really cool quantitative way of identifying an unknown compound by simply putting it in solution with something that it is soluble in, right? If you take organic chemistry next year, you will get to do this in the lab with a lot of organic molecules. It's one of the ways that you can confirm that you got the compound of interest because those changes will be known, and you can sort of work backwards this way. So this is why this is important. It's really important in lab. It has a lot of practical applications, and we're basically taking the concept that we just learned and using it in reverse, right? Okay, sample of organic compound. We're dealing with the same, it's supposed to be a T for temperature, same formula. We're dealing with freezing point. So we know we're going to deal with the freezing point constant, and we know we're dealing with molality and not molarity. We had a change in temp of 3.66 degrees Celsius. We are freezing benzene is our solvent, so 5.12. And our molality is the thing that we're solving for, and that'll be in moles per kilogram. And ultimately, we're trying to get to a molar mass of the compound. The molar mass of the compound. So we're going to have to do a couple more steps to get there, but let's start by first finding out what our molality is. So to do that, let's just rearrange our equation. We've got freezing temp divided by the freezing constant puts molality by itself. We were given a change in temp of 3.66, and the freezing constant of benzene is in the table, 5.12. Divide that out, gives us 0.7148. So we're not done. This is just our moles per kilogram. We were given 10 grams of benzene. So we have 0.7148 moles per kilogram equals however many moles per 0.01 kilograms. I'm just dividing 10 grams by 1,000. Is that right? 1, 2, 3, yes. 0.01 kilograms. So we can rearrange this formula. So I'll do it this way. We have X number of moles equals 0.7148 divided by 0.01 moles, kilograms cancel out. And we should get, excuse me, I took statistics with Professor Scribner, who was wonderful, and my math abilities should not be a reflection of his teaching ability. Um, he has a spiel about, or a whole lecture about math as language, and I want to be very clear that I am not fluent in math. I have found a way to get by, but it is not my first, second, or even my fifth language. So looking at those units again, moles per kilogram. Kilograms cancel out, equals moles. Okay, so we have our moles. We were given 1.35 grams of the unknown organic compound. We divide that by the number of moles calculated, gives us 188.85 grams per mole. And bonus points if you go online and find out what that is. And leave it as a comment. Alrighty. Question 52, a solution contains 5 grams of urea, a non-volatile compound, so again, it doesn't evaporate off and contribute to gas pressure, dissolved in 0.1 kilograms of water. If the vapor pressure of pure water at 25 degrees Celsius is 23.7 torr, what is the vapor pressure of the solution, assuming ideal solution behavior? This isn't that different from the osmotic pressure question that we were just dealing with, but we don't have to deal with the gas constant. That's actually not a great comparison. Forget I said that. So X solvent, this is going to be our mole fraction. And actually, let me back up a little bit further. Here is the equation of interest here. The pressure of the solution equals the mole fraction of solvent times the pressure of the solvent. We're solving for the mole fraction. And the mole fraction equals moles of solvent per total moles in the solution. So we have 5 grams of urea. We need its molar mass, which is 60.06 grams per 1 mole, equals 0.0833 moles of urea. We have 0.1 kilograms of H2O. Per kilogram, there are 1,000 grams. And per mole, there are 18.02 grams of water, which gives us 5.55 moles of H2O, of solvent. So finally, moles solvent per total moles is going to be our X solvent, our mole fraction, equals 5.55 over 5.55 plus 0.0833 equals 0.9852. All right, so we're part of the way there. Now we can plug in our pressure of the solution and the pressure of the solvent. Or rather, we can calculate for the pressure of the solution. The mole fraction we just calculated and the partial pressure of the solvent we were given was 23.7 torr, gives us 23.35 torr. So looking at this, does it make sense that the total pressure of the solution went down compared to the pressure of the solvent by itself? And if we think about vapor pressure's relationship with boiling points, then yes, if we lower the pressure of the total solution, then we need to add more energy to overcome kinetics so that it can then vaporize. Excuse me for just one moment. Okay. Arrange the following solutions by their decreasing freezing points. So we have 0.1 molar, excuse me, 0.1 moles of Na3PO4, 0.1 moles of C2H5OH, 0.01 moles of CO2, 0.15 moles of sodium chloride, and 0.2 moles of calcium. chloride. Since we don't know the freezing points off the top of our heads of each of these, we have to kind of infer them by the impact that they would have in aqueous solution, right? So that's the part that I wish was included in this prompt, is that we're putting all of these in aqueous solution, and how does that impact the freezing point of the total solution? And the reason that that distinction is important is because some of these will dissolve in water, and some of them will not. And we could even make this a little bit easier on ourselves and say, if we put them in a solution in which they are soluble, and then we don't have to look at solubility rules, because some of these that are soluble in water, sorry, not all of these are soluble in water. They will be soluble in other compounds. But for the purposes of this exercise, we're going to assume that they're all soluble. So they're going to break down into um, component parts. And so for sodium phosphate, we have two species basically. We have 3 sodium and 1 phosphate, and that gives us 4 total. And remember, the total concentration of dissolved ions in solution contribute to that change. So we have 0.4 moles of solute that are impacting the freezing point. For this carbohydrate, I'm going to go ahead and say that that's all one molecule. It's not soluble in water. So times 1, we're just dealing with 0.1 moles. 0.01 moles of CO2. CO2 is not, well, CO2 is not soluble in water. However, you should be familiar with the carbonic acid cycle. That's not what they're asking about right now. So we're just going to call that times 1. And for sodium and chloride dissociate in aqueous solution. So we have 2 species, gives us 0.3. So 0.15 times 2 gives us 0.3. And then we have calcium chloride. Chloride will dissociate from calcium. Chloride will also dissociate from itself. So we have 3 species of interest. So 0.2 times 3 is 0.6. And now we have a better sense of the proportional impact that each of these molecules will have on the freezing point of water. So the one with the greatest change to the freezing point is probably going to be calcium chloride, because we have that value of 0.6. So calcium chloride is 1, has a greater impact than sodium 3 phosphate, has a greater impact than sodium chloride, has a greater impact than this carbohydrate, which really quick, let me just stare at this for a second, and I'm going to cheat and use Google and try and remember what this is. It's ethanol. Meth F all. Yeah. And finally, CO2. So it's worthwhile to spend some time on those solubility tables and get familiar with those different species that are soluble in water and not, and just know how to chunk those, because recognizing that as 2 different species would be important. For example, you wouldn't want to put a break here between the phosphorus and the oxygens. Okay, I think this is our last exercise. Short and sweet today. And this is another osmotic pressure question. So with some physiological applications, which I love. So the osmotic pressure of human blood is 7.6 atmospheres at 37 degrees Celsius. This is around body temp. What mass of glucose is required to make 1 liter of aqueous solution for intravenous feeding if the solution must have the same osmotic pressure as blood at body temperature? 37 degrees Celsius, assuming ideal solution behavior. Lots of really cool details in this. We're given 1 liter, so we know whatever value we come up with for our, for our molarity, we don't have to do any calculations to figure out the volume. It'll just be however many moles, however many grams. So that simplifies things for us a little bit. It makes sense that we would want to pay attention to the osmotic pressure, right? Because we wouldn't want to, whenever we're putting a needle into a vein or an artery, and we're doing intravenous, right? So a vein, this is, if you're in the biology section, this is going to or away from the heart. This is going towards the heart. Anytime you put a needle in a vein, you have a direct line to the heart and the rest of the body. So it's important that we not mess with these things too much. um, or that we rather that we take these factors into account because they can have really, really profound physiological impacts. For example, if the osmotic pressure is not equal to, if it's really, really negative or really, really positive, we can actually pull nutrients out of the blood rather than and into the solution that we're trying to add, rather than delivering them to the tissues that we want to take care of here. So that the importance of this cannot be overstated. Again, this is an osmotic pressure question. So we're going to have molarity, gas constant, temperature, and our temperature is going to have to be in Kelvin. We're given, I already kind of alluded to the fact that we are interested in the molarity. We're given an osmotic pressure, we know our gas constant, and we're given a temperature. So we can really just plug these values in. We're given 7.6 atmospheres. Our gas constant is 0.08206. And our temperature was 37 plus 273 Kelvin, gives us our molarity, which is 0.2988 moles per liter. We're told that we're dealing with 1 liter of aqueous solution, so we can just keep on chugging with these moles of glucose. And for every mole of glucose, we have, I think that's 180.156 grams, gives us 53.82 grams of glucose going into that IV. If the osmotic pressure were too low, we could actually pull nutrients out of the blood. If it were too high, we could start messing with the osmolarity of the blood and causing other problems. And that is all I have for you today. I understand most of you will be watching the recording on the PSU YouTube channel or on the Twitch stream. It'll be available for a couple of days, I think. If you have any questions, feel free to email me. And have a great weekend. Get some sunshine on your eyeballs. Take care of yourselves. And we'll see you next week.